Welcome back to the deep dive. Today we're taking a deep breath and plunging into one of the most intellectually demanding areas of modern AI. We're talking about teaching a machine to truly understand an image without needing a massive amount of human-labeled data first.
It's really the quest for general-purpose computer vision.
The holy grail, you could say.
You could. And our source material today details a really significant step towards it. We're looking at a technical paper from Meta AI, from researchers including Jan LeCun, which introduces the image-based Joint Embedding Predictive Architecture.
Or JEPA for short.
Right, JEPA.
Now, that acronym might sound a little dense, but the mission for you, the listener, is pretty straightforward. We want to unpack how JEPA achieves these highly semantic image representations.
Meaning it gets the big picture, the concepts.
Exactly. It understands the what in the image, not just the pixels.
Oh, yeah.
And it does this while avoiding the two big fundamental compromises that have, really hampered every prior approach to self-supervised learning.
And to really appreciate the elegance of JEPA, we first need to understand the landscape it walked into. So at its core, self-supervised learning, or SSL, is about getting an AI system to generate its own training signals.
So it learns on its own without a human teacher.
Precisely. You can think about it using this energy-based model framework. The system is learning to assign a low energy score to things that are compatible, like two different views of the same cat, and a high energy score to things that are incompatible.
Okay, so that learning process is what builds these useful internal representations. So historically, how do we define what's compatible and what's not?
Well, historically, we've seen two, let's say, warring families of methods. The first one we can call invariance-based methods. These are systems you might have heard of, like SimCLR or Deno.
These are the ones that are famous for using all that heavy data augmentation, right?
Exactly. The core idea is you optimize an encoder to produce almost identical representations or embeddings for multiple artificially created views of the very same image.
So you take a picture, you crop it, you change the colors, and the model has to say, yep, still the same thing.
That's it. And it works. It does yield a high-level semantic representation, which is a big plus.
But you mentioned those handcrafted augmentations, the cropping, the scaling. That's one of the big headaches JEPA avoids. If they work so well, why is getting rid of them so important? What's the downside?
The downside is bias and rigidity. You're basically hard-coding a strong bias into the system. You're telling the model exactly what kinds of changes it should ignore, but those might not be the right things to ignore for a totally different task down the line. It's great for image classification maybe, but what if you switch to, say, instance segmentation? Your rules might actually be counterproductive.
And I'm guessing crop and scale an image doesn't translate very well to something like audio.
Not at all. It makes it really hard to generalize beyond images.
Okay, so that's family one. We get high semantic quality, but it's rigid, it's biased, and you need these architectural tricks like contrastive losses to stop the model from just cheating.
Cheating how?
Just, outputting the exact same thing for every single image, what they call representation collapse.
Exactly right. So then you have family two, the generative methods. This includes things like masked autoencoders, or MAE. They tried to solve that rigidity problem.
And how do they do that?
So these approaches, they remove or corrupt big chunks of the input, usually by masking out patches, and then the system has to learn to reconstruct the missing content.
Okay, so it's filling in the blanks.
Right, but it's filling them in at the pixel or token level. Very detailed.
That sounds much more general. It's relying on understanding the internal patterns in the data, not on a set of handcrafted rules.
It is more flexible, it requires less prior knowledge, and it generalizes better. But this is where the second major headache comes in. The paper points out that forcing a model to reconstruct every single missing pixel, the precise shadow, the tiny bits of texture, the color noise, it's just really inefficient.
And that inefficiency leads to what?
It leads to representations that are typically of a lower semantic level.
What does that mean in practice, lower semantic level?
So we measure this with a test called linear probing. Think of it as a quick checkup. You freeze the learned representations and see if a very simple single-layer classifier can perform well on a task using them.
And the generative models?
They usually underperform here. They've spent so much energy on getting the low-level pixel details right that they haven't efficiently compressed that knowledge into high-level concepts yet.
Got it. So we have this choice. Rigidity with high semantic quality on one side, and then flexibility, but with low semantic quality and sort of a distraction by pixel noise on the other.
And that is the exact gap that IJPA was designed to fill.
Okay, so this is where it gets really interesting. The core concept behind IJPA is actually rooted in these classic cognitive learning theories.
The idea that we learn by predicting.
Exactly. The idea that intelligent biological systems learn by constantly adapting an internal model of the world to predict what's coming next through our senses.
And that analogy is absolutely key. IJPA takes an approach that is fundamentally non-generative.
So instead of saying, here's part of an image of a dog, now draw me the rest of the pixels for the dog, what does it say?
It says, here's part of an image of a dog, now tell me what the abstract meaning of the missing pieces must be.
Whoa. Okay, that distinction predicting abstract meaning versus generating raw pixels, that seems like everything.
It is. Think about it like this. A generative model, like MAE, is like asking a detective to perfectly reconstruct a crime scene photo. They have to draw every blade of grass, the exact pattern in the mud. They get lost in the weeds, in the noise.
Right, all the irrelevant details.
IGI is different. It forces the model to learn a high-level summary. It predicts the output of another network, the target encoder, which has already processed and abstracted that image chunk.
So by predicting something that's already an abstraction,
You inherently throw away all the unnecessary, noisy, pixel-level details. The model is forced to learn the important stuff. What the object is, what its pose is, its relationship to everything else.
So let's talk about the architecture. How is this prediction machine actually built? You mentioned 2 encoders.
Well, 3 networks, really. First, you have the context encoder. This is a vision transformer, and it processes the part of the image that's visible, the part that we know.
Okay.
Second, you have the target encoder. This one computes the true high-level representation of the hidden or masked target blocks.
And what's the relationship between those two? They can't just be identical copies.
Right.
Otherwise, you run into that collapse problem again.
That's the critical part. You're right. To prevent collapse, the weights of the target encoder are not updated directly through backpropagation. Instead, they're updated using an exponential moving average, or EMA, of the context encoder's weights.
Okay, an EMA. Break that down for us.
Just think of it as a slightly lagging, smoothed-out average of the main network. This makes the target network a really stable, consistent reference point that the main network has to constantly try to predict. That asymmetry is what keeps the whole thing stable.
Very clever. And the third component bridges that gap.
That's the predictor. It's another, more lightweight network that takes the output from the context encoder, gets some positional information so it knows where the missing pieces are.
And then it tries to guess the output of that stable target encoder.
Exactly. And the entire system just learns by trying to minimize the error, the L2 distance, basically, between its prediction and the actual target representation. You're just trying to shrink that difference.
This whole framework sounds like it's incredibly dependent on what you choose to mask.
Yeah.
You can't just remove a few random pixels.
You are absolutely right. That brings us to the secret sauce. The success of IJPA is completely dependent on its masking strategy. It's how you guide the model to learn semantic things.
So what makes their strategy so special?
It's a multi-block strategy, and 2 things have to be true for it to work. First, the context block, the part you see, has to be large and informative. Think 85 to 100% of the image.
So you have a lot to work with.
A lot to work with. But second, the target regions, the parts you're trying to predict, also have to be large and numerous. Typically 4 target blocks, each taking up maybe 15 to 20% of the image.
So the model is forced to predict something substantial, a whole concept, like a wheel on a car, not just a few pixels of black tire.
Precisely. And now here is probably the single most important engineering detail in the whole paper. It's the thing that really confirms this conceptual leap we've been talking about.
Yeah, right.
The target blocks are masked from the output of the target encoder, not from the input image itself.
Wait, I need to pause on that. Why is masking the abstract representation so much better than just masking the input pixels, like MAE does?
Because if you mask the input, you are still fundamentally asking the model to learn all the messy physics of light and shadow when it tries to reconstruct what was there.
It's still getting bogged down in the low-level stuff.
Exactly. But if you mask the output, the prediction targets are already at a high semantic level because the target encoder has already done that first abstraction step for you.
And the data backs this up.
Oh, massively. The ablation studies are stark. When they tried masking the input instead, the linear probing accuracy just plummeted. It went from 67.3% top 1 accuracy down to 56.1%.
Wow, that's a huge performance gap. So that really proves it. The target encoder's job of creating that clean, high-level signal before the prediction even starts is the real magic here.
It is. By predicting the representation, you just bypass all the noise and you jump straight to the meaning.
So let's talk about the payoff. You put this all together, this clever architecture. What does it mean for actually training and using these models in the real world?
Well, the first and most dramatic payoff is just raw efficiency and scalability. IJEPA is incredibly resource efficient.
Because it's only looking at one view of the image, right? Not multiple augmented versions.
Exactly. That's a huge computational saving right off the bat. You're not duplicating all that work. And this allows for incredible speed. The paper shows that IJEPA converges in roughly 5 times fewer iterations than a reconstruction method like MAE.
5 times fewer. What does that mean in real-world compute time?
It's enormous. Pre-training a VT huge model, a really big one, requires less than 1,200 GPU hours. This makes IJEPA over 2.5 times faster than even a smaller model trained with IBOT, and over 10 times more efficient than the same huge model trained with MAE.
10 times. That's a number that fundamentally changes who can afford to train these massive models. But the big question, does it still maintain that high semantic quality? That was the weakness of the other fast methods.
And that's where IJEPA completely delivers. On that critical ImageNet linear probing benchmark our acid test, remember, it significantly outperforms reconstruction methods like MAE. And when you scale it up, it actually matches the performance of the very best view invariance methods like IBT on classification.
So it really does bridge that divide. You get the high semantic quality, the high efficiency, and you do it without any of those rigid, handcrafted biases.
And what's maybe most telling is that IJEPA isn't just good at classification. It actually shows superior performance on low-level vision tasks. If you look at benchmarks for things like object counting or depth prediction tasks that are crucial for robotics or autonomous driving, IJEPA actually surpasses the view invariance methods on depth prediction by a pretty significant margin.
That is compelling evidence.
Yeah.
It means the features it learns are just more general. They're applicable to a much wider range of problems.
And we can see this visually. The researchers used a framework to decode and visualize the latent representations IJEPA learned. And what they saw was that the decoded images consistently captured the high-level information, the objects, their pose, while just systematically throwing away low-level details and background noise.
So I took a photo of a tennis match and ran it through the IJEPA encoder. The decoded version would keep the players and the ball, but the exact shadows on the court might be gone because they're not semantically important.
Precisely. It learns what is conceptually necessary. It confirms that this abstract predictive mechanism is successfully filtering out the noise that hampers those other generative models. And that focus is what makes it so efficient and so broadly applicable.
So when we wrap this all up, what's the big takeaway for the future of AI training?
I think it's that IJEPA highlights this powerful and really effective new path forward. It's about achieving high semantic quality and superior efficiency by shifting the goal. You shift it away from the messy pixel space to this clean, abstract, learned representation space.
And you do it all while getting rid of those burdensome, handcrafted data augmentations.
Exactly. The key is that prediction in an abstract space just seems to avoid the core problems of the 2 previous approaches. And it's proven to be scalable. It gets better with more data and bigger models. It really feels like the right direction.
So a final thought then. If cognitive learning theories tell us that biological intelligence relies on predicting future sensory inputs in some abstract internal model, and IJEPA is now computationally proving that predicting abstract representations is far superior to reconstructing messy pixels, does this suggest a fundamental constraint? That for AI to achieve truly general-purpose intelligence, it has to learn to shed this obsession with low-level noise prediction entirely. Something for you to chew on until our next deep dive.